All right, ladies and gentlemen, good morning, good morning, good morning. So as I mentioned, it's going to be a short discussion. I'm trying to think. Today's Wednesday, I think. Yes, Wednesday. I want to just take a real quick look at Plan Book here. Okay, so yeah, basically, tomorrow's going to be very straightforward, very simple, no discussions. I got something for you. Excuse me. And then Friday is going to be discussion over section 3, and that's going to be our first math encounter. Well, now it's not letting me sign in. Okay. And then let's see what next week looks like. Yeah. This chapter is so short, I don't even have a quiz for you. What I've done is basically taken the section quizzes and turned them into just worksheets. I think that's a better option for this chapter. So, so next week, we're going to be done with this. We're going to get into the test next week. But today, we're going to look at magnetism from electricity. Again, just a very brief, kind of almost like an intro section to the rest of the chapter, because we're going to start looking at forces of electricity in terms of magnetism from here on out in this chapter. So what we just plan on doing, 2 small objectives. The magnetic field, we're going to describe the magnetic field produced by current in a straight conductor and in a solenoid. And then we're going to use what's called the right-hand rule to determine the direction of the magnetic field in a current-carrying wire. Now, there's going to be 2 right-hand rules that we're going to utilize in this chapter, except they're going to be slightly different and used for different purposes. But they're going to be great. Every time we do this chapter, never fails. And in the test, I always see people doing it during the test. So it's always good to know that you're practicing what you're learning. Anyway, the magnetic field of a current-carrying wire, when we have a long, straight current-carrying wire, it's going to have a cylindrical magnetic field. Okay, so basically, any wires that are run through a building, if you will, they are going to have, as long as they have current going through them, a cylindrical magnetic field. And we can use compasses if we want to, and we can use those to show, and I got a picture of this, the direction of the magnetic field induced by the wire. But if you don't have a compass, we can always utilize the right-hand rule. And that way, if you're bored and you're just really curious, you find yourself somewhere and you're like, I wonder where this magnetic field is going and what direction the current's going in. All you got to do is the right-hand rule. So basically it looks like this. If you take your pen or pencil in your hands, do so like I am, okay, just like this. So what is happening is we have current flowing through our pen or pencils, and it's going from the bottom through the top, okay? So you see your thumb is indicating the direction in which the current is flowing. Your fingers, as they wrap around your pen or pencil, is the direction in which the magnetic field is moving. So as you grip it like this, you notice your fingers are curling counterclockwise. That is the direction that the magnetic field is in a current-carrying wire. Okay? If the current was going in the opposite direction, well, it'll work that way too. Okay? Going in the opposite direction. So very simple, but useful when it comes to worksheets and tests in this chapter. Here's your magnetic field indicated by compasses. As you see, they've removed the insulation. Okay, that's honestly the best way to identify the magnetic field. Insulation does just that. It insulates a lot of the internal components of a wire. And so removing that insulation in this little piece, we have a little ring of multiple compasses, or if you just have one compass, it will sit there and track the direction of that magnetic field. As you see here, these are all going in a circular motion around that wire. Now, solenoids are objects that you most likely use on a day-to-day basis. What these do is these produce a strong magnetic field by combining several loops. Now, if you recall from the video on Friday where they did that homemade electromagnet with the little AA battery, the nail, and the copper wire, you saw how that copper wire was wrapped around that nail. It was very, tight in these coils, these loops around that metal nail. The closer you have them and the tighter you have them together, those copper loops, the greater the magnetic field can be produced. That's really how solenoids are going to be useful in their applications. And really what it is, it's just a long helically wound coil of insulated wire. But oftentimes, we place something else inside of that loop, okay? Oftentimes, it's a metal rod. Just depends on the application. Some examples where we see solenoids are an old tiny doorbell. Okay, these days you have digital doorbells. Okay, you have wireless doorbells that just use a digital chime. But if your household still has the old kind where it's got the box and it's got the little chimes inside, metal chimes inside there, what happens is a hammer is actually hitting those chimes. And it works by a person pressing the doorbell button. That completes a circuit. The circuit allows for electricity to flow through there, and it flows through a solenoid. That solenoid then produces a magnetic field. That magnetic field then is what kind of makes the metal rod or the hammer go in and out and strike your chimes. So very simple application, but we also have car starters that use solenoids. Okay, so you do that every day. Certain locks, a lot of times of really strong locks, certain bank vault locks, or any similar application where they need basically the control of electricity to operate the locks. Car locks are another example, okay, where solenoids are going to be of use in this. But if you look at this is a very important image to know, okay? Look at the magnetic field and the direction of the current. Over here, we've got the current going in on the left side, and it coils around, and exit the opposite side. The place where the current enters, that is basically our north pole, if you will. If you recall from the first section that the direction of the magnetic field flows out of the north, back around to the south, and all the way back through that solenoid out the north again. It's just a complete cycle, okay? If the current's coming in from the right side downwards, again, that field will flip and go the opposite direction. That means that the south will become the north pole and vice versa on the opposite. I put emphasis on that picture because you will need to demonstrate that in the not too distant future, okay? Now, I told you that today was a very short discussion. You can stop crying now because it's so short, okay? Coming into section 3, we are going to, again, be getting into the math portion using the word Tesla, as we saw in the video as well, as a means to calculate magnetic force and all that good stuff. So, today, I'm going to say while it's on recording, today, I'm going to hand out that second worksheet I wanted to yesterday. It's going to be, it's called, like I said, it's called section quiz. That's not the right one. Concept review, there it is. Still based off of section 1, okay? And so you'll want to make sure your notes are out for that. Tournament in class tomorrow for those of you who are here. If you are at home, if you've already done it, go ahead and submit it online. Otherwise, you can submit it tomorrow. It won't count it as late. To the same post from yesterday. And that is all for today. So I'm going to cancel the recording.